I'm Jake, and today I'm going to take you through the Physics Mechani Kit. For the Physics Mechani Kit, we've prepared 5 different activities. Those activities are the vector demonstrator, the force meter, the movable pivot balance, the Atwood machine, and the sliding friction activity. Each of these activities and all of the kit materials for every activity comes in the Mechani Kit. And with these materials, teachers will be able to design even more activities than the ones that we've detailed. But these 5 that we've detailed, we've prepared worksheets for, and today I'm just going to kind of quickly run you through each of the activities. It's worth noting that what the activities look like are, in their form, currently prototypes for the most part. Due to the coronavirus, we weren't able to manufacture our final kits, and we weren't able to get all the materials that we needed to fully finish and demonstrate these prototypes today. So bear in mind that the final products will look slightly more polished and refined than what I'm about to show you. Just to jump in, the first one I'm going to show you is the vector demonstrator. Now, in the vector demonstrator, here you can see, if you look down, what we've set up is a block supported by 2 different rubber bands. With these rubber bands, the block is currently in tension. Students will be able to move this block around on this pegboard, and by using strings and by using straws to cover up these rubber bands and only show the stretch length of the rubber bands, they'll be able to calculate the resultant vectors applied by moving this block in different directions. If you initially put the block in a position like this where it's in tension, by moving the block to one side or another, the resultant vector is always going to point back towards the equilibrium point. This will get students experience with visualizing vectors and trying to see how to calculate resultant vectors based off multiple vectors. Now, here's the force meter that students will be using. If you look closely, you can see that there's a rubber band on the inside of a tube. For the final kit, there will also be a paper ruler taped to the inside of the tube so that students can actually visualize the change in length of the rubber band. Students will use this force meter, and they'll use the weight kits provided to calibrate that force meter. What we don't have today are the buckets that support the weights, but by hanging a weight on the end of the force meter and measuring the change in displacement, students will be able to calibrate the spring coefficient K of their force meters. Now for the next activity I'm going to show you, it's the movable pivot balance. So what students do in this activity is they take their pegboard and put it in a vertical orientation like you see here, and then they're able to take a ruler, and they have weights attached to the ends of the ruler supported at different distances. And so students predict if the weights are equal but the distances of string are different, neglecting the weight of the string, whether that ruler will stay in equilibrium when it's applied or whether it will shift. So we can kind of demonstrate that right now. If we attach the ruler at its center, even though the strings are different weights, or different lengths, as long as the weights are the same, the ruler maintains equilibrium. The next thing I'll show you is the sliding friction activity. So in this, students also use a vertical orientation of their pegboard, and then they're able to use the ledge that's provided. This ledge has a rough sandpaper side and then a smoother side. And now, with the rough sandpaper side facing up, the students will attach the ledge to their pegboard as seen, and they'll take a block which has a smooth side, and they'll use that block and slide it down the pegboard. They wait, and they have to find the location in which the block will actually slide. So, because that coefficient of friction was too high at that angle, we have to go to a higher angle in order to get the block to slide. Now, if we slide the block down the ramp, the students can measure the time it takes the block to slide down, compare that to the time they would expect in a scenario with no friction, and calculate the static friction coefficient between this block and this ramp. Finally, the last activity is an Atwood activity. Unfortunately, today we don't have the pulley required to fully demonstrate this activity, but students will utilize a ledge, as you see here, and they'll also utilize a pulley for this activity. So if we remove the dowels here, and we set it up as they will when they actually do the experiment, what they'll do is they'll take the ledge It's easily inserted. And then they'll attach a pulley around here. They'll take their block, which they can drag across the ledge, and by hanging weights from the end of the pulley, they can find the weight, the minimum weight required to get the block to actually move across the ledge. Using this weight and principles of the pulley, the students will be able to calculate the static friction coefficient between the block and the ledge. Now they can also use this, instead of having it set up like a ledge, they can use a pulley with a ramp orientation, or they can use many different variations of the Atwood activity using these kit materials. Now, as you can see, the activities that I've shown you today can be used in many different orientations to illustrate many different principles than the ones that I've shown. We encourage students and even teachers to develop activities that they think can further reinforce difficult physics concepts with these manipulatives. But like I said before, we provided worksheets for each of the activities. We thank you for your time and thank you for watching this demonstration.